Thanks everybody who's here. I wanted to quickly start off actually by requesting you to type in something into chat, not just to the panelists, but so that all attendees here can see it, to kind of gauge where we're at, where we're coming from, and what we hope to get out of this the next 30 minutes, if that makes sense. Just off the cuff, without thinking too deeply about it, what is one word, technique, or emotion? What first comes to mind when you hear the word or the phrase active learning? Let's take no more than 20 seconds here. I see engagement several times over, hands-on, stress, something fun, some discussion, group work, students, something that's lively, something that's challenging, something based off of constructionist learning, it sounds like. A lot of good things. Okay. And I think this scroll that we see going through the Zoom chat is actually pretty indicative of the idea of active learning in general. There are certainly lots of techniques that come to mind for a bunch of instructors. There are some techniques that I think really do work pretty well in large kind of canonical lecture hall settings. I basically only work in large lecture hall settings of 200 to 250 students at the introductory statistics level. And certainly think pair shares can work in those situations. Lots of in-class polling via some student response system can be really valuable. And then there are other active learning activities that maybe don't find as easy of a home in those settings. Minute papers or muddiest point reflections, which I actually have found to be very valuable when I've worked with classes of 30 to 40 students. You might ask a student to, at the end of a lesson, take no more than a minute on lined paper to write down what they thought the high-level points were of an engagement, or what was the muddiest thing going on that didn't make sense over the course of the day together. Those can be really valuable to kind of promote students' metacognition, to think about where they are in terms of the content that was covered. Certainly, there are some activities that are really kind of well-placed at the K-12 level, four-corner or jigsaw activities that I've struggled to figure out a way to use in a large lecture hall. Similarly, active learning has a whole bunch of terms associated with it that I often hear people using interchangeably. Some people call it active learning, others call it student-centered learning, maybe learning through play, project-based learning. I have heard it called activity-based learning as well, basically the same thing. I've got a colleague who jokingly says that active learning is anything more than listening, if that makes sense. And that worries me a little bit because oftentimes when I'm teaching my introductory stats courses, I'm a little worried that listening might not even be happening at all. And so what I wanted to do over the course of the next 20 minutes or so is talk through a heuristic that I really like when deciding how I build out my lectures in large classes, and then walk through an example from start to finish. The definition that I most like for active learning, that might even be a little bit too broad, was by von Lohen-Eisen in 1991, that says it's a method of learning in which students are actively, or interestingly, experientially involved in the learning process, and where there are different levels of active learning depending on that student involvement. And that is actually something that was very important for me back in the day, where I initially thought, well, either you are not learning or you're actively learning, and it was this dichotomous idea. And over time, I found that there is actually a gradient in terms of how engaged students are, and that oftentimes I don't need them to be maximally engaged in something. Sometimes partial engagement is actually quite useful. The heuristic that I want to talk about is actually really old. It's called Edgar Dales' cone of experience, and it was from back in 1947. This heuristic that really isn't terribly perfect, and I think has some numbers that are kind of arbitrary in it, but is nonetheless proven very useful for me when I'm designing lessons. The heuristic, or this cone of experience, is trying to identify how much people remember of communications they're presented by way that it's presented to them, if that makes sense. So for instance, he made the argument that people generally remember only about 10% of what they read, which is really unfortunate because I do give a lot of pre-reading assignments before class. What's maybe even worse is that they really only remember about 20% of what they hear. And this drives me nuts because I often find myself telling students, well, didn't you remember the announcement I made at the beginning of class or something along those lines? But nonetheless, these two ways of communicating and these two ways of teaching oftentimes results in students being able to define a term, list out different examples of a term, describe it or explain it. Oftentimes learning engagements that are only either written or audio don't promote any kind of learning beyond kind of the lower levels on Bloom's taxonomy, if that makes sense. Dale's heuristic continues, claiming that people remember about 30% of what they see. Humans are a little bit more visual than they are audio or verbal in many cases. And they actually remember 50% of what they hear and see. He had this interesting argument that if you combine the two senses, something that's not just a written assignment, but also a demonstration maybe, you can actually get a little bit more retention and you can get them to a higher place on Bloom's taxonomy. Maybe they can demonstrate an application of statistics, apply it in practice, or something along those lines. Continuing on down the heuristic, they can remember 70% of what they say and write, and 90% of what they actually do. And I think that's kind of the key thing that we're going for here when we're trying to create active learning engagements for students in large classes. How can we get them to situations where they're actually participating in the statistics we're teaching in hopes that they can later analyze it, design an experimental study, create new statistical content, or evaluate and critique statistical findings. The reason why I like this heuristic so much really is because it helps me organize how I want to present certain learning objectives for my class. My argument is that when I was initially teaching, I wanted everything to be active, everything to be kind of colorful, wondrous, rainbows and ponies or whatnot, the most incredible class every minute of that class. And I think over time, I've realized that there are certain learning objectives that take priority over others. For instance, a more important learning objective for me is I want students to be able to explain why the precision of a statistic as an estimate of a parameter increases with the size of your sample. That's something that's important enough for me to try and place at the bottom of this pyramid. This is a foundational idea for the life science students that I teach, and I need to make sure that when I teach this learning objective, I do so in a way that models the real experience, that actually has students actively engaging in this idea. As an example of something that I do teach but don't care as much about, there are oftentimes students who want me to justify the decision to divide by n-1 rather than n when computing the sample standard deviation. And while that's important for some students, it's not that critical to me. And so that's something that I can throw into a footnote in my lecture slides. I can send them out to a YouTube video kind of explaining it in more detail and kind of relegate that learning objective a little bit. What you'll notice about this heuristic is that it kind of separates the different ways you might teach something into verbal-based methods, visual-based methods, and then finally that participatory method. I think this maps on really well to the idea of passive versus active learning, and kind of brings me to a good point where I want to start looking back at my lecture. How do I actually go through those active learning assignments, if that makes sense? And the example that I want to walk through is called statistical unicorns, or at least that's what I call it in front of my students. And it's based off of this phrase that I first read in a book by Andrew Gelman and Deborah Nolan that said, you can load a die, but you cannot bias a coin. They say in the introduction of this passage, the biased coin is the unicorn of probability theory. Everybody has heard of it, but it has never been spotted in the flesh. And as with a unicorn, you probably have some idea of what a biased coin looks like. To kind of walk you through what this activity looks like step by step by step, on a Wednesday in class, in lecture, I actually asked a couple students to come up to the front and give them a coin much like the silver dollar that you see in front of you. It's deformed in some way. And I asked them this question. Because this coin is deformed, do you think it may be biased in favor of landing a particular side when flipped? And if so, why? It's a quick think, pair, share, and we ask students to identify where they fall across three potential hypotheses. Deforming the coin makes it biased in favor of landing concave side up, convex side up, or really doesn't do anything, doesn't bias the coin when flipped. We asked students to kind of submit their initial opinions via Top Hat, and I think this is last semester's data, this past spring's data. About half of the class thought that something going on with the physical properties of coin flipping, once you deform it or bend it, would make it biased in favor of landing concave side up. Moreover, we asked a couple other Top Hat questions. The first one is that in small group meetings or in recitations that they'll get to later in the week, they're actually going to receive a deformed coin and record the result of 30 coin flips. The question that we ask students before they do that is that if the coin was exactly or perfectly unbiased, how many flips would you expect to land on the convex side up? Most students correctly identify that you should be getting 15 out of 30 heads or tails or concaves or convexes, which means they're usually ready for the next, I think, more important question. We actually give them 2 or 3 questions to kind of talk with their neighbors about this. How many flips would you need to land convex side up to decide the coin was, in fact, biased? And the results here are actually pretty messy. We can display them in front of class almost immediately after students have submitted them and talk about the distribution of what students think is convincing evidence and isn't convincing evidence. There are always students who like to point out this, the very few, the small number, who think that 15 does not give evidence the coin is unbiased. We talk about the idea that quite frequently, semester over semester, there are always some students who require a perfect 30 out of 30 and rarely 0 out of 30, even though they're mathematically identical, along with various other attributes of this distribution. That usually closes out our lecture, and then we later in the week have them meet in small groups of about 30 to 40 students with a graduate teaching assistant. Over the course of about 15 minutes, they answer a bunch of questions in a worksheet, and then eventually actually run a simulation where they receive a deformed coin. We take laundry tokens and we actually bend them in a vise that I have in my garage, and ask them to record the number of those 30 flips that land concave or convex side up. Right here, you see the results for a class of 130 that I teach from this spring. Their average sample proportion was 47 or 48% landing concave up, with a standard deviation of about 17 or 18%. Now, what's interesting is that we can then push them out to a shiny applet. That shiny applet allows them to simulate doing this process thousands and thousands of times over, and then compute an empirical p-value. They not only compute the p-value for their own results, but also other hypothetical sample results. Once they've got that, we, for the first time, introduce the terminology of p-value, which we teach on a gradient scale. Students then identify that if their p-value is greater than 10%, they have little evidence of bias by deformation of the coin. If it's between 1 and 5%, or it's between 5 and 10%, we say that there's some evidence against bias, and so on and so on and so on. Now, of course, as we saw on the previous slide, because most students got a p-hat value between 40 and 60%, most students ended up with little evidence of bias. Kind of a direct contradiction of what they had initially hypothesized in class the day before, where more than 50% thought that it would be biased in terms of the concave side. Before they leave this small group activity, though, we asked them to do one more simulation. They've already flipped the coin 30 times, but we next ask them to spin it on a tabletop. I admit this is somewhat chaotic for GTAs initially, but you can see the results displayed below are radically different here. And that's in part because I've hidden the ball here, and I've discovered, due to a physicist friend, that the physics involved with center of mass and a bunch of other things I didn't really understand greatly influence a spun coin, but do not really affect a flipped coin. And so at this point, by the end of recitation, every student had a sample statistic for the coin and the flip trial they had done, along with a sample statistic for the spin trial they had done. However, they had not yet seen the whole class results that we've been looking at over the past couple slides. When they returned to our large lecture hall, again, sitting all kind of 130 of them together, we asked them to write out some responses. If we think about our original question, does deforming a coin bias it when flipped? How would you answer that question if you only considered your own data? And when you look at the class results projected at the front of a lecture hall on a big screen, along with a summary of how many received little evidence of bias, some strong, very strong, extremely strong, would your conclusion be the same or different? We then repeat that same think, pair, share and writing out process for the spinning trial. Would you conclude that a spun coin that is deformed is biased, given your own results or given the whole class results? Students usually every single semester almost uniformly conclude that a coin is not biased when flipped, but it is biased when spun, if that makes sense. And I think that's a reasonable conclusion based off of the data that they've gotten over the course of this activity. Now, what's nice about this particular kind of sequence of events is that you can actually return to this data several times throughout the semester in later chapters. For instance, we almost always return to this idea when we first talk about effect sizes. I make the argument that if both have bias, or both a spun and flipped coin may have bias, but simply of different magnitudes. We discuss effect size and the idea of the power of a statistical test at n equals only 30. Additionally, we explore the problem of the winner's curse and other problems in low-powered studies, if that makes sense. And usually this ends up being kind of a cool activity for a number of reasons beyond that, just because students are able to come back to where they fell in the distribution relative to their peers. I like to say that emotion drives attention, which in turn drives retention. And the fact that having a fun data collection activity in a small group setting is usually something that's socially bonding in many classes where students don't otherwise learn one another's names as well, can really promote how engaged they are in learning thereafter. That's basically the example that I have for you guys right now. And I suppose I'm running about 3 minutes faster than I did, or than I had intended to, but I want to open up the floor now to questions, comments, follow-ups that you have just based off of what I've talked about so far. I think I can go to chat just in a moment.
Well, first, John, thanks very much for a very engaging presentation. I invite people to send some questions into the Q&A, and there is a few questions coming in. And the first one is, you talked about the sort of pyramid, and how do you use that to decide how to efficiently use your time? So I guess the idea being you want people sort of at that active retaining a higher percentage. So when you're devising your class, how does that work in your mind to how much time should I spend doing various things as I prepare for the class?
I think that that's a great question. And I think if I understand it correctly, if we kind of go back to this heuristic, one thing that, or another way that I can go through all of the learning objectives that I have for the class and kind of categorize them in terms of what's something that's worth turning into a more active assignment and what is something that is not as worth making into an active learning assignment is, I'm not going to be able to remember the source for it, but the ESOL categorization method. There are the most important learning objectives that I want them to learn for in a lifelong way. That's my L learning objectives. There are some learning objectives that I want them to be able to demonstrate independently. That's my I. There are some that I want them to be able to do with support. Maybe that's notes, maybe that's in a collaborative setting, but that's my S. And then finally, there are my learning objectives that are simply ones I want them to know exist. That's my E. And so that ESOL methodology, or it could be LIES if we go from most important to least important, helps me categorize where in this pyramid I should be developing my learning materials. Is that answering your question?
Yeah. So a second question, John, a couple of people have typed in regarding how would this activity differ if you weren't in the large class setting, you were in the small class, let's say 25 to 30 student setting?
Oh, that's a great question. So I might have skipped over a couple components of the activity. So if we're only looking at a class of maybe 30 to 40 students, certainly what we need to do is have everybody repeat this study several times over, and the data collection process is a little bit longer. Also, one thing I try and enforce in my large lectures is to have students sit in different places in the lecture hall among different students every single time they arrive. Anecdotally, I find that students, if you don't prod them, will otherwise tend to kind of coagulate to the same seat every single time that you meet over the course of the semester, and so don't really learn the names of anybody other than the people in their immediate vicinity. And I really do think that one of the things that fosters really strong think pair shares in a large lecture hall is not having a think pair share with the same person over and over and over again, because the informality can grow to be a bit too much, and I think the urgency of being able to communicate your ideas to somebody you don't know as well falls off, if that makes sense.
We also have a question, John, that asks about how long does it take to do the actual data gathering from students get the coins, students flip the coins, spin, register the data, etc.
That's a great question. So this is their first engagement into hypothesis testing, and also the first time they start using Shiny applets in our class. We use them quite frequently moving forward after this activity. And the data collection process is probably at most 12 or 13 minutes, I'd say, maybe 15 if the GTA is moving a little bit slower. But really that small group recitation is usually an hour-long period, and so there are other components of the activity built in around the data collection process, either familiarizing themselves with the idea of a resampling distribution, doing a little bit of reading on introducing p-values and things like that.
Sort of along those lines, there was a very practical question of how do you get all these bent coins? And how do you make them? And if you do, how do you make them? And so on.
That's a great question. That is a one-time capital investment. I think I have a collection of about 400 of these coins that I bent maybe over the course of an hour and a half in my garage. I use laundry tokens, which cost like $10 for 100 on Amazon or something like that. I'm not the main problem is that they're heavy when you're transporting them all in a single load, if that makes sense. But I'm sure there are other kind of similar manipulative questions where you're doing a one proportional resampling test, basically, that don't require you to front load this kind of weird bent coin activity. The reason why I like to use the bent coins in particular is because a lot of the students who I teach in these life science gateway courses in statistics have taken statistics at some point in their life, which means at some point they've engaged with a textbook that asks them to suppose a coin had a 70% chance of landing on heads. And so everybody is kind of familiar with this unicorn of statistics, this thing that's usually presented to teach a binomial distribution or the normal approximation to it. And I think usually students really grab onto it as a consequence.
There was a request by a couple of people if you could expand a little bit on, and you actually have the slide up right now, so the slide that goes through the cone of experience. Mm-hmm. If you could just say a little bit more about that, I think maybe they're really interested in just that sort of hierarchy of how it goes from that 10 to 20 to 30, et cetera.
Yeah, so I definitely think, so again, like I really like using this heuristic as a way for me to sort my own brain in terms of, I really need help and I need support structuring what I think is important and critical for students to remember for a long, long time after leaving out of the class. What are things that I want them to be proficient in, at least while they remain undergrads in some kind of hard science major? And what are the things that I just want them to know exists and be able to reference, in fact, in the event that they do have a specific question about it later down the line. And so the reason why I like this heuristic, even though it's certainly not perfect, is that it reminds me that if I find something to be really critically important, I can't just present really, really good lecture notes about it, because really, really good lecture notes are likely not going to get done what building some kind of active learning engagement around that same idea would. The 10%, 20%, 30, 50, 70, 90, those percentages I think are just Edgar Dales numbers and are not particularly well tested or in any ways meant to be interpreted with like a force majeure, if that makes sense. But they do remind me that if I want to really engage students or really help them understand why a t-distribution is slightly different than a normal distribution, the fundamental idea behind least squares regression, I really need to make sure that they are engaging and exploring those ideas either with simulations, with applets that allow them to drag data points around or something along those lines, so that it sticks with them a little bit more.
Kind of related to that, the same person wanted to know if you could speak a little bit to your learning objectives for that particular activity that you discussed.
Yeah, that's a great question. So it's the first activity that we do for inference. It's our introduction to hypothesis testing. Before we introduce random variables, before we formally define hypotheses in terms of a known alternative, we don't have any parametric tests at this point in the class. It happens in week 2.5, basically, of the semester, although that's somewhat changed with the move to remote learning. But our goals for students, just based off of this activity, are to understand the idea of a null model, in so many words, without understanding the definition, without being able to connect it to the definition, understanding that a null model describes the variability of a random process under a single important assumption. You're assuming that this coin is unbiased and playing out what the possible values of the sample statistic are.
So this question is near and dear to my heart because I think it's something I run into also, and I think a lot of people do. So the question is, how can you encourage students to participate in these more active learning activities? Maybe it's just my experience as a student in TA, but a lot of students seem to resist these kinds of active learning activities, and it can become awkward.
That's a great question. Yeah, so I do think that that is something that stumps me as well, if that makes sense, and it is near and dear to my heart, if that makes sense. I think a couple things that come to mind right off the bat are the fact that I insist that groups never be larger than 4 students. That seems like a kind of small and arbitrary rule, but in my experience, the 5th student just cannot pull their full weight, can very easily kind of coast through an activity and not really get all of the value out of it that they might be able to. And so a simple thing is groups can never be larger than 4. The second thing, I know this was discussed a little bit in the clicker presentation last session. I give graded points for everything. There's very little participation points in a lot of these activities because I think that a lot of students who aren't fully engaging in assignment might get over that hill if they knew it was worth a couple points graded on accuracy.
We got time for a couple more. So one of them is, do you tie this to active assessment in any way?
Oh, that's a great question. So in our large lecture courses, we haven't figured out how to do that just yet. We still give most of our summative assessments as pen and paper exams. We have some formative assessments that are arguably more active learning engagements where students have peer-to-peer writing assignments or they have, we're just starting out with these assignments called elaborate ×2 assignments where a student has a prompt. One student will respond. A second student needs to is required to elaborate on that first student's response. An example of that might be, here's a data set, compute its standard deviation, and then alter it to make it larger. The first student does that, and then the second student needs to do that in turn, and then describe or justify why that particular change does that.
And this will be our final question. It says, in a very large class, I can imagine having the students measure the degree to which the coin is bent, and then checking to see if that might be an important covariate in their analyses. Have you thought of that? Have you done that?
I have thought of that, or rather, many students have thought of that, and we haven't pursued the idea further. I definitely agree that there are a lot of students who, while I know that an earlier question said some students really don't find a lot of comfort in active learning assignments where the answer isn't as clear, the objectives might not be as clear, and they're just kind of asked to play in a sandbox and figure out for themselves what they find important and what they find valuable. There are other students who kind of just go nuts in those instances, and they start thinking about how bent the coin is, whether the coin was minted in a certain location, does that influence stuff? And it really kind of sets them loose to think creatively about this random process, the assumptions that are being made by the null model, and kind of downstream effects like that.
All right. Thank you, John, for your presentation. And thank you to everyone for your very active engagement in the presentation and all your questions and chats.